Good morning, everyone. Okay. Okay, so before we go all crazy and talk about how deep neural networks will eventually replace all of you physicists, what I want to do this morning is to take a step back and to discuss about how we actually do science. And to do that, I will start with this illustration, which for me is really the typical science experiment. So this is what is known as the Galton board. It's a toy which is usually made to illustrate the central limit theorem, but this is not what I want to do today. What I want to do is the following. Let's say this is what I observe from nature, and then as a physicist, even though I'm not a physicist actually, I'm a computer scientist, what I want to do is to describe what I'm observing. So I want to build a model that would fit with my observation. Okay, and so one way to do that would be to say that, okay, I will just maybe model the trajectory of all these balls within this lattice. And how I would do that, I would say that every time one of these small balls hits one of the pins, then it goes either to the right with some probability that I have to define, let's call it theta, or it goes to the left with 1 minus this probability. And then it reaches the next level, and then the same random choice happen again until eventually it reaches one of the bins. Okay? And then what I do is that, okay, I can build this experiment, and then I can collect observations. Okay? And then what I would like to do is to do inference, so to determine what is actually this probability of going right, or 1 minus this probability to go left. Okay? And the way to do that would be to say that I have to define what is the likelihood, what is P of X, what is the probability of reaching, for example, that bin, given that precise probability value, that precise parameter value. Okay? And the way to do that would be, for example, just to integrate over all random trajectories that could lead me to that bin. Okay? And then I would sum all these probabilities together, and that would give me the likelihood of reaching this bin. Okay? And if I'm smart enough, then I would notice that, okay, maybe I can rewrite this integration over all these trajectories as actually a binomial distribution with some parameters theta. Okay? And from which I would be able directly to evaluate the likelihood of my data. So I could do that, but let's say now I remove one of these pins. Okay? Then it would no longer simplify as a binomial distribution. But still what I could do is just to integrate over all the random paths from the start to that bin, and if I just sum all of them together, weighted by their corresponding probability, then this would give me the probability of reaching this bin. Okay? And this is actually usually what is done in physics, except that you don't have a very simple model like this. What you want to do is to describe nature, and your model, for example, is the standard model of particle physics. Okay? And what you do as physicists is that you write simulators, computer programs that can generate forward trajectories from, for example, collisions of two particles up to what you would observe or what you expect to observe in an actual detector. Okay? So the setup is the following. We start with a simulator, which for me is a theoretical model, a physics model. Okay? It comes with some parameters, for example, the constants that you are interested about, and this simulator is random. Okay? It involves some stochastic processes such that you can generate observables X, and every time you run the simulator, you will produce different observables X. Okay? And so if you go from the left to the right, then this is what we call prediction. Okay? According to your model, you expect to see this observable X. And this is just following your mechanistic forward model that you have defined yourself as physicist. But however, what you want to do often in science is the opposite. We start with observables, and then we want to rewind the simulator from the right to the left and to do inference on the model parameters. Okay? And in this scenario, this is quite complicated because we don't have a direct access to the likelihood function P of X given theta. Why? Because we would have to integrate over all these random trajectories. And usually there are just too many of them for this evaluation to be tractable. But still, we need this piece of information then to do inference on the parameters theta of, for example, our model. Okay, so as an illustration, I will start with the standard model of particle physics, which you can represent in this single slide, and it comes with 19 parameters. Okay, and what you do then is that you write a big, gigantic simulator that will involve the generation of the event and then the collisions of two, let's say, particles. And what would happen after that? It would decay into many, many other particles that would each interact with the materials of a gigantic detector that you would build around the point of impact. And then you could also simulate how each of these particles will interact with the electronics, and then you could simulate what you expect to see in the software that you would run on this data. Okay? So you could do all of these things, and then what you do as physicists is that you actually build this experiment to test your theory. Okay? So you go back after a few years, once you submitted your paper, which describes, for example, the standard model of particle physics, you build the experiment, and then you eventually collect data. Okay? So the setup is really the same. We have model on the left with some parameters. We have a simulator with everything that I've described. And then we have the actual experiment through which we'll actually collect data. And then what we want to do is to do inference. So given the data that I collect, for example, in this detector, I want to do inference on these 19 parameters of the standard model of particle physics. And of course, this is quite complicated because I would need to integrate over all possible ways I could actually see this particular observable in my detector. Okay? And so in the case of particle physics, you end up with this big integral, which is the likelihood of observing some observable X in your detector, which is the result of you start with some theoretical parameters, and then from this you can generate parton level momenta, which would correspond to some latent variable. Let's call them ZP. And then these parton level momenta would decay into showers. So they would split and they would produce even more other particles at random. Let's call them ZS. And then each of them would interact more or less at random with the detector. And then you could also simulate what you would eventually record as data and how you would ingest this data in your software to eventually produce some observable X. Okay, so that means now if I want to do, for example, maximum likelihood estimation on the parameters theta, the 19 parameters of my model, given this particular observable X, I would need to evaluate this likelihood. And that means I would need to integrate over all these Z variables. Okay, and that's just too complicated to do. Okay, so fine, we have this problem. What can we do? Well, when you look back at what we need in terms of statistical inference, we'll usually need a few key ingredients. It could be that we need the likelihood, but in our case, it's just too complicated. We don't have access to it. But fortunately, you can also use other key ingredients, and one of them is called the likelihood ratio, which is a ratio of two likelihoods. Okay? So for example, the ratio where you set the parameters of your model to some values theta 0 over the likelihood over that same data, but for some other values of the parameters. Okay, and if you manage to have access to this likelihood ratio, then usually you can do also statistical inference. If you are Bayesian, the other key ingredients I would like to compute is the posterior, which is P of theta given X. And then what is really important, and this is one of the messages today, is that in this likelihood-free scenario, or in this simulator-based scenario where the only thing you have is you can generate samples, actually each of these ingredients can be approximated with modern machine learning techniques, even if you don't have labels, even if none of these quantities are known at training time. Okay, you can learn them even if you are never able to evaluate them at training time. Okay, so how do we do that? Well, what I will do is that I will consider this second key ingredient, the likelihood ratio. Okay, and actually, when you look at supervised learning or just binary classification, it will provide a way to automatically learn this likelihood ratio. Okay, so for example, what you can do is that you take some neural networks that you decide. Okay, and what you do is that you first generate sample X from the first hypothesis. So you set your simulator with some parameters theta 0, and then you generate just many sample X. Okay, and you label all these samples with class 0. And then you do the same for samples that you generate from the second parameters value theta 1. Okay, and you label each of them with the class 1. And then what you do is that you train the classifier to distinguish data between the two classes. Okay, and you would do that, for example, by minimizing the cross entropy as you would do with a neural network. And then if you did your job correctly, what you will end up with is the optimal classifier. And we know from the theory of statistical inference that the optimal classifier corresponds to the ratio of the likelihood of the data for the for the hypothesis theta 1 over the sum of the likelihoods. Okay? And that means if I manage to train this object, if I manage to obtain this quantity, then I can use it to get back my likelihood ratio. And one way to do that is to take 1 minus this neural network over the neural network, and then I will obtain back the likelihood ratio, P of x given theta 0 over P of x given theta 1. Okay? So that's quite powerful because that means I can use supervised learning neural networks to obtain a quantity that I cannot evaluate at training time. Okay? Once I have this quantity, this likelihood ratio, which is given as the output or some transform output of my neural network, now I'm able to do inference. So, for example, you can invoke Will's theorem to draw exclusion contours from this likelihood ratio, and then you can, for example, exclude theories that will not agree with the data. Okay, and so this is exactly the way it was done, for example, to discover the Higgs boson, where what physicists did is that they did not build a neural network, but they built a summary statistic that approximated the likelihood ratio, and then from this likelihood ratio, then draw exclusion contours to eventually be able to reject the hypothesis in which the Higgs boson does not exist, therefore it exists. Okay? Okay. Another important message is that, okay, supervised learning, I can use it now to do likelihood ratio estimation. So that means every time you need to do inference, you can just import everything we've been doing in the field of deep learning. So all these fancy architectures that computer scientists have been developing, like graph neural networks, of course, convolutional neural networks, and many, many others, you can use them if you manage to, if they fit with the kind of data you have to, you observe, you can use them then to do inference. Okay, so this is just one method that we have been working on, but we've actually contributed to a few others that are defined in this table. I will not go over each of them, but the main message is that, okay, you could just generate this sample from this from your simulators and then train this neural network, but it could still be very inefficient in terms of how many samples you would need to generate before you obtain a likelihood ratio which is good enough to make good inference. And you can actually accelerate this process if you go inside your simulator and then extract some auxiliary information about, for example, the joint likelihood of some data and then some particular trajectory that you took when you generate that piece of data to then use that at training time to build better likelihood ratio estimators. Okay. So you could use that to do frequentist kind of inference. You can actually use the same kind of machinery if some of you are Bayesian. So when you do Bayesian inference, what you are usually interested in is in computing the posterior, so P of theta given x, which is defined by the Bayes rules as the product of the likelihood P of x given theta. This is the thing you can sample that you have access with your simulator, times some prior that you define over the model evidence. Okay, and in this case, we are in a scenario where we have two sources of intractability. The first one is that we cannot evaluate the likelihood in the first place, because for the same reason as before, we would need to integrate over all random trajectories. And then this model evidence, we cannot evaluate it either, because we would need to integrate over all model parameters data. Okay, so the way it's usually bypassed in Bayesian inference is that you do MCMC, where in MCMC you would compute ratios of the posteriors, and when you do ratios of posteriors, this model evidence will cancel, and so you would just need to be able to evaluate the likelihood and the prior. Okay, so that would be fine, but in this case we are in a setup where we cannot even evaluate the likelihood. Okay, so what do we do? So one of the usual techniques to do Bayesian inference in this likelihood-free scenario is called approximate Bayesian computation, and it's very, very easy to understand. You start again with your simulator that takes as input some parameters, but then you define a prior over these parameters. Okay? So what you will do is that you will draw first some random parameters value from this prior, you will inject them into your simulator, and then you will produce data. Okay? And then you compress this data into a summary statistic, okay, which is a function that you have to define. And then on the other hand, you also have collected some observed data. You also compress them into the same summary statistic. And now you will compare the two summary statistics, the one that you have simulated and the one that you have observed. And then if the distance or some distance that you have to define between this vector of summary statistics is small enough, then you keep this parameter value theta. And then you repeat. Okay? So for some of the theta parameters, they will pass this test. So you will say that they agree with the data they observe. And if they don't pass this test, then you just discard this parameter's value. And then you repeat this procedure over and over. And then what you do is that you say that the distribution of accepted parameters value theta corresponds with the posteriors that I want to approximate. So this is fine, but this is quite inefficient, okay? Because you can imagine that many of these parameters value will not agree with the data, okay? And then also in this procedure, you have to define how do you actually compress the data, what is the summary statistics function that I should use, and once I've decided that, how do I compare two vectors of summary statistic? What is the distance between the summary statistic? And then what is this epsilon that I should consider? Okay. So there are many problems, but still people have been using this kind of algorithms, not in physics, but in other fields of science, like in population genetics, where this algorithm was invented. What we propose instead is to amortize the Bayes rule. Okay, and it's based exactly on the same observation, is that if you look at the Bayes rule, which relates the posterior as a ratio of the likelihood times the prior over the model evidence, you can rewrite this guy as a likelihood ratio, the likelihood over the model evidence, times the prior. Okay, it's not exactly a likelihood ratio. In this case, it's likelihood to evidence ratio, but still it's the same thing. Okay. And again, what you can do is to use a neural network. You can use supervised learning to learn P of x given theta over P of x. And the way you would do it is, again, by sampling x from the likelihoods, and you would label all this x value with label 0, and then you would sample x from the model evidence. You would label each of them by the class 1, then you would learn a neural network to distinguish between the two, and then that would give you, you could transform then the output of this neural network to get back the likelihood to evidence ratio. And now that you have this piece of information, every time you just want to evaluate the posterior, what you can do is that you can just feed the data into your neural network, you obtain the likelihood ratio, you multiply that output with the prior, and that gives you a direct and amortized evaluation of the posterior. Okay, so this is for the theory. Now I want to finish my talk with a few examples from physics. So the first actual use case we have applied these techniques to is in the case of particle physics, where what we wanted to do is to study extensions of the standard model of particle physics that were parameterized by two parameters, this one and this one. And so what we did is that we first compared the usual type of analysis that would rely on histograms, then to draw exclusion contours, and you would find this kind of limit in orange. If you use one of the techniques that I've talked about today, for example, the one where you just train a classifier, you'd obtain the curve in green, and you see that eventually you would obtain something which is better than the histogram-based analysis. And then if you use one of the techniques where you go inside the simulator to extract more data, then you reach better performance by using fewer training samples. Okay? And then in terms of the exclusion contours, you obtain this kind of plots, where based on histogram, you would have the orange contours, For this particular problem, you can actually compute the theoretical contours that you would expect, and they are represented in gray. You cannot really see them because our techniques, for example, in red, is exactly on top of these gray contours. So it's working quite well. A second example is the one of dark matter substructures from gravitational lensings. So if dark matter exists, then there should be halos of dark matter that surrounds and permeates galaxies. Okay, and this halos it's itself constituted of several subhalos. Okay, and each of them will interact with the light that goes through them. Okay, so that means that they will have an effect, if that exists, on the gravitational lenses that I do observe in the universe. Okay, because they will bend the light that goes around that. Okay, and so what we did there is that we started with a model that would define the distribution of these subhalos in a halo of dark matter around some host galaxy, and this distribution would be defined by two parameters. And then what we did is that we wanted to do inference. Given some observation, given this kind of images, we want to do inference on these population parameters. And again, you can use the same machinery to do exactly that. Okay. So in the paper, we did the two versions, the frequentist version, where we would draw these exudent contours, but we could also do exactly the same if we want to do Bayesian inference. And in the case of Bayesian inference, we would obtain these kind of plots, where as you, of course, add more and more observations, then your posterior gets narrower and narrower, okay, which you observe. This is the posterior. Okay, a third example, which is work in progress, is the one of constraining the mass of the dark matter particle, which is basically answering the question, if dark matter exists, then we have to define what is its mass. So should we prefer either cold dark matter theory or the theory in which the dark matter is warm? Okay, and one way to do inference or to put constraints on the mass of the particle is through the observation of stellar streams. So if this is a galaxy, what you see there is a stream of stars. And again, if dark matter exists, then there will be subhalos, and these subhalos will have an effect on the stars, on the objects that are part of these streams. Okay? And there will be part of them where some density, some masses is missing because it has been kicked out by the dark matter around it. Okay? And again, we can define a simulator to simulate this kind of data, and then given the some of the stellar stream we do observe, we can do inference and put more constraint on the mass of the dark matter particle. Okay, and again, this is some preliminary plot, but for example, and this is for toy data. But if this is the kind of observation that we have, where we describe a stellar stream as a density, okay, then we can derive an approximate posterior, and then from this posterior, we can draw credible intervals, for example, to exclude some of the masses of the dark matter particle. A last example is the one of fast parameter estimation for gravitational waves. And again, it's the same story. We have a simulator with 10 or 12 or so parameters. It describes very well the kind of observation we make, but it's usually very, very slow. So what astronomers have been doing there is that they've been using MCMC to do parameter estimation on the actual observations. And so when they make plots with final discovery result, then to make this plot, it actually take in the order of a month of computation, because they just have to run MCMC for many, many iterations. And of course, what you propose there is we can approximate the posterior very, very quickly with a neural network, which has learned to amortize directly with respect to the marginals that we want to look at. And so we can reduce from a month of computation to just less than a second. Okay, so to summarize my talk today, what I want to say is that much of modern science is based on likelihood-free simulations. So the thing that you start with is a simulator from which you can generate data. Then the likelihood ratio is a key ingredient that you can use to do statistical inference, regardless of your religions. By that I mean you can do frequentist kind of inference or Bayesian inference. You will need this quantity for the two kind of inferences. You can use supervised learning to learn this object, to learn the likelihood ratio. That means you can import everything from deep learning to do that. And then if you manage to go inside the simulator, then that can also help you a lot in terms of how many samples you would need to build these ratio estimators. Finally, I want to thank some of my collaborators, Kyle, Juan, Johan, Yuri, Antoine, Arnaud, and Szilárd. Thank you. Which algorithm? You mean the neural network that we'll use to approximate the ratio? Well, usually the bottleneck will always be the simulation. It's usually very, very slow.
Okay, but do you have understanding how the speed scales with the dimension? Is it exponential?
That depends on the problem. I mean, there might be parameters that have no effect on the resulting ratio, and so.
Okay, maybe we have time for one more question if there's anyone. If not, then let's. Yeah.
I was wondering, is there any future development? You think your procedure is final, is established, or you see some weak points where you say you could further improve this?
Yeah, so one of the main issues is that we know that the ratio that we'll build will never be perfect. So all this story is nice when we know that we'll obtain this optimal classifier. In practice, we'll not find it. So what does that mean in terms of the kind of inference we do? How does that error propagate into the inference procedure? That's something which is still unclear so far.
Okay, let's thank Gilles again for his talk.